When discussing whether or not a function is differentiable, in other words, whether or not the derivative exists at a certain value, we can see that it's a good way of looking at it is to determine whether or not the function is locally linear. Okay, because differentiable functions are locally linear at a particular point. So what does it mean to be locally linear? Well, as you see here, it's talking about a function is locally linear if it resembles its own tangent line very close to the point where x is equal to a. Okay, in essence, if we can turn a curve into a line by zooming in enough at a point, then the derivative exists at that point. We can say the function is differentiable at that point. Right. So let's take a look at this graph. F of x is x times the cosine of 3x. Right, so I've got this. I'm going to pull my graphing calculator. Right, you can see here I have x times cosine of 3x. Just ignore this for a second. All right, we're going to take a look at the graph. So I'm going to do zoom and then choose option 7 for trig, since we got ourselves a trig function. If you're doing this on your own calculator, you want to make sure that you're in radians. Right, we hit enter, and here is the graph of, it was over there so slightly, of x times the cosine of 3x. Okay, so there's a lot of waves going on in this function. Now we're particularly interested when x is equal to 2. All right, so let me hit the trace button for a second, and I'm going to type in 2. All right, so we can see that we're interested up at that point right there. Okay, so let's zoom in on this point and see what happens. So I'm going to hit my zoom button. I'm going to zoom in. All right, it's saying you want to zoom in close to 2. It won't let me go exactly to 2, but this is close enough. Yes, I do. So I'm going to hit enter. And when I do, it's going to take a second, but in a moment, you're going to see the top of that hill. There it is. All right, I've zoomed in when x is equal to 2, and then there's the next one. All right, so I'm going to just move my bullseye over just a touch. All right, get it close to 2 again right there. And the cool thing about the graphing calculator is if you hit the enter button, it repeats the last command. So the last command was to zoom in. So if I hit enter again, I'm going to zoom in again on this top of the hill. So remember, right now we've got the hill. All right, we zoomed in. Now we're going to zoom in even more on this area. Watch what happens. All right, it takes the calculator a second to think about it, but we've zoomed in some more on that hill. Okay, and we're going to keep doing this. Okay, because the idea is, can we turn this curve into a line if we zoom in enough? So again, I'm going to modify my bullseye just a little bit so that it's back on the blue line. Notice that x is more or less equal to 2. And when I hit enter, again, I'm going to zoom in some more. And now, when I zoom in, I've got an ever so slight of a curve going on there. Okay, and just move my bullseye. And just to go one more time, we're going to see that, in fact, yes, now what I've done is I've taken that curve, and we had a lot of curves going on there, and I've turned it entirely into a line. Okay, so I have made the graph locally linear. Okay, I've basically zoomed in enough to turn this very curvy function into a line. What this means is that the derivative will exist when x is equal to 2. We can say that our function is differentiable at x equals 2. Okay, and again, the idea is that the tangent line should match up with this. So I'm going to go back for a second to y equals, and I'm going to activate this second function. I'm not telling you what m and a are. It's not really that important right now, but I want you to see something. I'm going to activate this. So the red line that you're going to see, let me zoom trig again, is the line which is tangent to our function. As you see, it's being drawn when x is equal to 2. Remember, our point is somewhere right around here, and here comes our tangent line. Okay, so that line comes up, it just grazes the curve ever so slightly at x equals 2, and then keeps on going. Now, let's zoom in again one more time. So I'm going to hit trace and option 2, or enter 2 for enter to get my butterfly up there. Okay, and I'm going to hit the zoom button, and I'm going to zoom in when x is close to 2. And when I do that, okay, remember we're going to get the little hill now. It's going to come up. We'll get some more stuff going on here, and then we'll see our line in a second. And we can see that it is, in fact, still tangent when x is equal to 2. I'll modify the bullseye just a touch, and hit enter again to zoom in some more. And notice what happens between the blue curve and the red line. Okay, there's the curve, and in comes the tangent line in 1 second. Okay, see that they almost overlap? But if I zoom in even more, hit enter one more time, maybe a second time, we'll see. There's the curve, and here comes the tangent line. One right on top of the other. Okay, and if I do it one last time, we see we're going to get, the blue is going to get entirely covered by the red. Just takes a second to, it's got to graph the entire function. And there it is. All right, so the red just overlapped the blue. We get ourselves a little bit of purple there. Okay, so what happened? The function, all right, resembled its own tangent line when we got very, very close to 2. Okay, so therefore our function is locally linear. Okay, and that means that basically f prime of 2 exists. That's what we were able to show with our graphing calculator. Now, we don't know what it's equal to yet, okay, but we do know that it exists. At the moment, what we're trying to look at is what are situations where the derivative may not exist. Okay, and you're saying, well, why could the derivative not exist? Well, ultimately, remember the derivative, this is our alternate form, the definition of the derivative. Our derivative is a limit. And we know that limits have instances where they don't exist. And so if we can find out when these limits don't exist, then we find out when the derivative doesn't exist. So the next video, we'll talk about the particular cases.